Let's begin our discussion for lecture 15, focusing on LP convergence.
Let's begin with the definition of convergence in LP. Let P be greater than or equal to 1. We say that a random sequence X, which maps from our sample space omega to the space of real valued sequences R to the N, all defined on a probability space omega, script F P converges in LP to a random variable X infinity, which maps omega to R, if the limit as n tends to infinity of the LP norm of the difference x sub n minus x infinity is equal to 0. This LP convergence is denoted by writing limit as n approaches infinity of x sub n equals x infinity in LP. Just a reminder for everyone, for P in the interval 1 to infinity, including 1, the convergence of a random sequence X from omega to R to the N in LP to random variable X infinity from omega to R is equivalent to stating that the limit as n tends to infinity of the expected value of the absolute difference X sub n minus X infinity, all raised to the power P, equals 0. An important proposition states that LP convergence implies convergence in probability. So if we consider P in the interval 1 to infinity and a sequence of random variables X defined on our probability space omega script F P such that the limit as n approaches infinity of X sub n equals x infinity in LP, then it must also be true that the limit as n approaches infinity of x sub n equals x infinity in probability. The proof is quite straightforward. For any epsilon greater than 0, we can apply Markov's inequality to the non-negative random variable given by the absolute value of x sub n minus x infinity, all raised to the power P. This tells us that the probability of the set where the absolute difference x sub n minus x infinity greater than epsilon is less than or equal to the expected value of the absolute difference x sub n minus x infinity raised to the power P, all divided by epsilon to the power P. Since the numerator tends to 0 for LP convergence, the probability also goes to 0, establishing convergence in probability. Now, let's consider an example to illustrate that convergence almost surely does not necessarily imply convergence in LP. We'll work with our familiar probability space, the unit interval from 0 to 1, equipped with the Borel sigma algebra on this interval, and the Lebesgue measure lambda, where lambda of any subinterval from A to B is simply B minus A. We define a sequence of scaled indicator random variables x sub n mapping from omega to the set containing 0 and 1 such that x sub n of omega is 2 to the power n times the indicator function of the interval 0 to 1 over n evaluated at omega. Let n be the set containing only the point 0. For any omega not in n, meaning for any omega strictly greater than 0, we can find an integer m defined as the ceiling of 1 over omega. For all n greater than this m, x sub n of omega will be 0. Since the Lebesgue measure of n, the single point 0 is 0, this implies that the limit as n approaches infinity of x sub n is 0 almost surely. However, if we examine the LP norm, the expected value of the absolute value of x sub n raised to the power P is calculated as 2 to the power np times the length of the interval, which is 1 over n. So we get 2 to the power np divided by n. For p greater than or equal to 1, this expression clearly does not converge to 0 as n tends to infinity. In fact, it diverges. Thus, we have almost sure convergence to 0, but not LP convergence. As we recall, convergence almost surely implies convergence in probability. Therefore, the example we've just walked through also serves as a counter example to the idea that convergence in probability might imply convergence in LP. It does not. Let's now turn to the L2 weak law of large numbers. Consider a sequence of uncorrelated random variables, x mapping omega to r to the n, defined on our probability space omega, script f, p. We'll assume that the expected value of each x sub n is mu, and the variance of each x sub n is sigma squared for all n in the natural numbers, defining the sum s sub n as the sum from I equals 1 to n of x sub I, and the n empirical mean x bar sub n as s sub n divided by n. The theorem states that the limit as n approaches infinity of x bar sub n is equal to mu, both in L2 and in probability. To see why, we look at the variance of x bar sub n. Due to the uncorrelatedness of the random sequence x and the linearity of expectation, the variance of x bar sub n, which is the expected value of x bar sub n minus mu all squared, can be rewritten as 1 over n squared times the expected value of s sub n minus n mu all squared. This simplifies quite nicely to sigma squared divided by n. Since sigma squared over n clearly goes to 0 as n approaches infinity, it follows that the limit of x bar sub n is mu in L2. And of course, since convergence in LP, in this case, L2 implies convergence in probability, the second part of the result, convergence in probability, also holds. There is also an L1 weak law of large numbers. For this version, we consider an IID random sequence x defined on our probability space with the conditions that the expected value of the absolute value of x1 is finite and the expected value of x1 is mu. Again, defining s sub n as the sum of the first n terms and x bar sub n as the empirical mean s sub n over n, we find that the limit as n approaches infinity of x bar sub n equals mu, this time stated as convergence in probability. Now for another illustrative counterexample, convergence in LP does not necessarily imply almost sure convergence. We'll use our standard probability space, the unit interval from 0 to 1 with its Borel sets and the Lebesgue measure. For each natural number k, let s sub k be the sum of the integers from 1 to k, which is k times k plus 1 all over 2. We then define integer intervals I sub k as the set of integers starting from s sub k minus 1 plus 1 up to s sub k. It's clear that these intervals I sub k, as k ranges over the natural numbers, form a partition of the natural numbers. So every natural number n will fall into exactly one of these intervals, say I sub k sub n. This means we can write n as s sub k sub n minus 1 plus some I sub n, where I sub n is an integer between 1 and k sub n inclusive. Therefore, for each natural number n, we define an indicator random variable x sub n of omega as the indicator function of the interval from I sub n minus 1 over k sub n to I sub n over k sub n evaluated at omega. This is the classic sweeping or typewriter sequence. For any omega in our unit interval, x sub n of omega will equal 1 for infinitely many values of n. This happens because any given omega will be covered by these shrinking and sweeping intervals infinitely often. As a result, the limit superior of x sub n of omega is 1, and thus the limit of x sub n of omega as n goes to infinity does not equal 0. In fact, the limit doesn't exist for most omega. However, this sequence does converge to 0 in LP. The expected value of the absolute value of x sub n raised to the power p, which is just x sub n, since it's an indicator, is simply the Lebesgue measure of the set where x sub n of omega is 1. The length of this interval is 1 over k sub n. As n tends to infinity, the corresponding k sub n also tends to infinity. So 1 over k sub n tends to 0. Thus, x sub n converges to 0 in LP, but not almost surely. Let's move on to some cornerstone L1 convergence theorems. First, we have the monotone convergence theorem. Consider a non-decreasing, non-negative random sequence x mapping omega to the non-negative reals to the n, defined on our probability space such that each x sub n is in L1, meaning its expectation is finite. Let x infinity of omega be defined as the supremum over n of x sub n of omega for all omega in our sample space. The theorem beautifully states that the expected value of this limit x infinity is equal to the supremum over n of the expected values of x sub n. In essence, for non-decreasing, non-negative sequences, you can interchange the supremum and the expectation. For the proof, one direction is fairly immediate. From the monotonicity of the sequence x, we know x sub n of omega is less than or equal to x infinity of omega for all n and omega. By the monotonicity of expectation, the expected value of x sub n is less than or equal to the expected value of x infinity. Taking the supremum over n on the left side directly gives that the sup over n of exn is less than or equal to ex infinity. For the other direction, let alpha be any constant strictly between 0 and 1, and let y be any non-negative simple random variable such that y is less than or equal to x infinity. We then define a sequence of events E sub n as the set of all omega in our sample space where x sub n of omega is greater than or equal to alpha times y. These E sub n are, of course, measurable sets in script f. From the monotonicity of the sequence, x sub n is non-decreasing. It follows that the sequence of events E sub n is also monotonically non-decreasing. Furthermore, their union as n goes to infinity, the entire sample space omega, assuming y is not identically 0, in which case the result is trivial. Consequently, alpha times the expected value of y times the indicator of E sub n is less than or equal to the expected value of x sub n times the indicator of E sub n, which itself is less than or equal to the expected value of x sub n. We then leverage the fact that the limit as n tends to infinity of the expected value of y times the indicator of E sub n is simply the expected value of y. This relies on the monotone convergence theorem applied to the sequence y times indicator of E sub n. Thus, taking the limit, we find that alpha times Ey is less than or equal to the supremum over n of Exn. Since this inequality holds for all alpha in the open interval 0.1, we can let alpha approach 1 from below. And since it holds for all non-negative simple functions y that are less than or equal to x infinity, we can take the supremum over all such y. By the very definition of the Lebesgue integral, the supremum of Ey over such simple functions y is precisely Ex infinity. This gives us the desired inequality Ex infinity is less than or equal to the supremum over n of Exn, which completes the proof.
Next, we have Fatou's lemma. Consider a sequence of non-negative random variables x mapping omega to the non-negative reals to the n defined on our probability space. Let x infinity of omega be defined as the limit inferior as n tends to infinity of x sub n of omega for all omega. Fatou's lemma provides a very useful inequality. The expected value of this limit inferior x infinity is less than or equal to the limit inferior of the expected values of x sub n.
To prove this, we define a new sequence of random variables y sub n, where y sub n is the infimum of x sub k for all k greater than or equal to n. It follows that this sequence y sub n is non-negative and importantly non-decreasing as n increases. Furthermore, x infinity, which is the limit inferior of the x sub n sequence, is precisely the supremum of this y sub n sequence, which is also the limit of y sub n as n goes to infinity. Now we can apply the monotone convergence theorem to our non-negative, non-decreasing sequence y. This tells us that the expected value of x infinity, which is the limit of y sub n, is equal to the supremum over n of the expected values of y sub n, which is also the limit of Ey sub n. The final step comes from the monotonicity of expectation and the definition of y sub n. Since y sub n is the infimum of x sub k for k greater than or equal to n, it must be that y sub n is less than or equal to x sub k for all such k. Therefore, the expected value of y sub n is less than or equal to the expected value of x sub k for all k greater than or equal to n. This implies that Ey sub n is less than or equal to the infimum over k greater than or equal to n of Ex sub k. Taking the limit inferior as n goes to infinity on both sides, noting that limit Eyn is Ex infinity, we get Ex infinity is less than or equal to the limit inferior of the infimum, which is simply the limit inferior of Ex k. Our third major L1 convergence theorem is the dominated convergence theorem. Let X be a random sequence defined on our probability space omega script f p. We assume that this sequence x sub n converges almost surely to some random variable x infinity. Furthermore, and this is the crucial domination part, suppose there exists a non-negative random variable y, which is in L1, meaning its expectation Ey is finite, such that the absolute value of each x sub n is less than or equal to y almost surely for all n. If these conditions are met, almost sure convergence and domination by an L1 function, then the expected value of x infinity is equal to the limit as n tends to infinity of the expected value of x sub n. In other words, domination allows us to interchange the limit and the expectation. For the proof from our hypothesis that the absolute value of x sub n is less than or equal to y, it directly follows that y plus x sub n is non-negative almost surely, and similarly y minus x sub n is also non-negative almost surely. Now we can apply Fatou's lemma to these two sequences of non-negative random variables. For the sequence y plus x sub n, Fatou's lemma tells us that the expected value of the limit inferior of y plus x sub n, which is e of y plus x infinity, is less than or equal to the limit inferior of the expected value of y plus x sub n. By linearity of expectation, this becomes e y plus e x infinity is less than or equal to e y plus the limit inferior of e x sub n. For the sequence y minus x sub n, similarly, e of y minus x infinity is less than or equal to the limit inferior of e of y minus x sub n. This translates to ey minus e. X infinity is less than or equal to ey plus the limit inferior of e of minus x sub n, which is ey minus the limit superior of ex sub n. From the first inequality, we can cancel ey since it's finite to get ex infinity less than or equal to the limit inferior of ex sub n. From the second inequality, after cancelling ey, we get minus ex infinity less than or equal to minus the limit superior of ex sub n, which implies that the limit superior of ex sub n is less than or equal to ex infinity. Combining these two, we have the limit superior of ex sub n is less than or equal to ex infinity, which in turn is less than or equal to the limit inferior of ex sub n. For this chain of inequalities to hold, the limit superior and the limit inferior must be equal, and both must be equal to ex infinity. This means the limit of ex sub n exists and is equal to ex infinity, which is what we wanted to show. Now let's extend these powerful convergence ideas to conditional expectations. Let x be a random sequence on our probability space omega script f p such that the expected value of the absolute value of each x sub n is finite for all n, and let script g and script h be event spaces, specifically sub-sigma algebras of our primary sigma algebra script f. Then analogues of our convergence theorems hold for conditional expectations. First, we have the conditional monotone convergence theorem. Consider a random sequence x that is non-negative and non-decreasing almost surely. We define x infinity of omega as the supremum over n of x sub n of omega for each omega. If this pointwise limit x infinity is in L1, meaning its expectation is finite, then the conditional expectation of x sub n given script g converges upwards almost surely to the conditional expectation of x infinity given script g. Next, we have the conditional Fatou's lemma. Consider a random sequence x that is non-negative. The slide also says non-decreasing almost surely, which is a stronger condition than typically needed for Fatou, but we'll follow the text. If the limit inferior of x sub n is in L1, then the conditional expectation of this limit inferior of x sub n given script g is less than or equal to the limit inferior of the conditional expectations of x sub n given script g, all holding almost surely. And thirdly, the conditional dominated convergence theorem. Consider a random sequence x and a non-negative random variable y that is in L1 such that the absolute value of x sub n is less than or equal to y, almost surely. This domination must hold for all n in the natural numbers if in addition the sequence x sub n converges to some x infinity almost surely, then the conditional expectation of x sub n given script g converges to the conditional expectation of x infinity given script g. This convergence happens both almost surely and in L1. Let's briefly outline the proofs for these conditional versions. We begin with a random sequence x where each x sub n is in L1. For the conditional monotone convergence theorem, by the monotonicity of x sub n, the sequence of conditional expectations E of x sub n given script g is also non-decreasing almost surely. Thus, it converges almost surely to some script g measurable random variable. Let's call it y. The standard monotone convergence theorem then implies that for any set g belonging to the sigma algebra script g, the expected value of y times the indicator of g is equal to the limit as n goes to infinity of the expected value of the indicator of g times the conditional expectation of x sub n given script g. By the defining property of conditional expectation, the taking out what is known property, this is the limit of the expected value of the indicator of g times x sub n. Applying the standard monotone convergence theorem again, this limit is the expected value of the indicator of g times x infinity. Since this equality, expectation of y times indicator g equals expectation of x infinity times indicator g holds for all g in script g, it must be that y equals the conditional expectation of x infinity given script g almost surely. For the conditional Fatou's lemma, we define a sequence y sub n as the infimum of x sub k for all k greater than or equal to n. This sequence y sub n is non-decreasing and converges upwards to y infinity, which is the limit inferior of x sub k. By the monotonicity property of conditional expectation, the conditional expectation of y sub n given script g is less than or equal to the infimum over k greater than or equal to n of the conditional expectation of x sub k given script g almost surely. Then applying the conditional monotone convergence theorem to the sequence y sub n which converges to y infinity, we get that the conditional expectation of y infinity given script g is the limit as n goes to infinity of the conditional expectation of y sub n given script g. Combining these, this is less than or equal to the limit inferior as n goes to infinity of the conditional expectation of x sub n given script g, almost surely. Finally, for the conditional dominated convergence theorem, we apply the conditional Fato's lemma to the non-negative sequences z plus x sub n and z minus x sub n, where z is the dominating L1 random variable y. This yields that the conditional expectation of z plus x infinity given script g is less than or equal to the limit inferior of the conditional expectation of z plus x sub n given script g, almost surely. A similar inequality holds for z minus x sub nan. The conditional expectation of z minus x infinity given script g is less than or equal to the limit inferior of the conditional expectation of z minus x sub n given script g, almost surely. These two inequalities combined with the linearity of conditional expectation lead to the conclusion that the conditional expectation of x sub n given script g converges to the conditional expectation of x infinity given script g, almost surely. The L1 convergence part requires a bit more but follows from the domination. These convergence theorems are fundamental tools in probability theory and its applications. We will see them used frequently. That concludes the lecture.